Hello there, Mr. Sutton here, bringing you this lesson on the trapezoidal rule. In this one, we will be using trapezoids to determine the area under a curve. For your warm-up, pause the video and write the area formula for a trapezoid. So that's going to be area equals 1/2 height, parentheses base 1 plus base 2. Or another way of writing this, you could add the two bases together, then divide by 2, and then multiply by the height. I actually prefer this one over here, but whichever one you want to use. Either way, we're going to now estimate the area under a curve using trapezoids. And this is the trapezoidal rule, estimating by finding and adding area of trapezoids. So our best approximation in the short run, at least, given a limited number of rectangles, was MRAM, at least up to now. But now you notice, if we draw some trapezoids under a curve, because we're allowed to have slanted tops instead of just the flat top of the rectangle, we can close in on a lot more of that space that we used to kind of just leave behind. The downside of this is the trapezoid formula a little bit more complicated than the rectangle area formula. And if you'll notice here, all of these trapezoids are sideways, so the base in the trapezoid formula is actually the y value of your function, while the height of the trapezoid is going to be the delta x of your function, the subinterval length. Let's try out an example for one of these. So we're going to now find the area under x squared on the interval from 2 to 10 using the trapezoidal rule on 4 subintervals. We'll start like with LRAM and RRAM and MRAM by making a table. So for this one, since I'm using basically the left and the right endpoints of rectangles, but now they're going to be trapezoids, I'm going to do the same setup as I did for LRAM and RRAM. So I'm starting at 2, and to get from 2 to 10, I'm going to go by 2s. So we got 4, 6, 8, and 10 for the x values. And then the y values that go with that, they're just perfect squares. So 4, 16, 36, 64, and 100. And now, to approximate the integral from 2 to 10 of f of x, again, we're writing approximately equals because this is an approximation. We're going to do some trapezoids. So I'm going to have the y values 4 and 16 added together over 2 times a base of 2. So this is base 1 plus base 2 divided by 2, just averaging the bases and multiplying by the height here. And we'll do another one together. So the next one we're going to have 16 plus 36 over 2 times a base of 2. Pause the video and see if you can figure out the other two things that we have to write down here. All right, let's see if you got it. So now we have 16 plus 64 over 2 times 2, and 64 plus 100 over 2 times 2. All right, now let's go ahead and simplify this. Now, as always, on a free response on the AP, this would actually be good enough, assuming that you put any units that need to be on there at the end here. But if we need to simplify it, we can do so. So let's see, this is going to be, all these 2's divide by 2 times 2's are going to cancel out in at least this problem. So we end up with 20, 52, this is 100, and 164 all being added together. So let's see here, that's going to be 72, 172, and then we're going to have, let's see, 336. There we go. We'll do one more approximation with the trapezoidal rule. For this one, you're approximating the integral from 0 to 11 of the function whose selected values are given in this table. Pause the video and see if you can get this one. All right, so we've got to do our trapezoidal rule. We've got, for our first area that we're adding up, we've got negative 2 plus 6 over 2 times a base of 2. And again, we're writing approximately equals here. Next, we've got 6 plus 4 over 2 times a base of 3, because 5 minus 2 is 3. Next, we've got 4 plus negative 1 over 2 times a base of 1. And then we've got negative 1 plus negative 8, or minus 8, over 2 times a base of 5. And let's go ahead and simplify it if we need to. So these 2's are going to cancel. This is just going to be 4 for that first area. For this next one, we've got essentially 5 times 3, which is 15. Here we've got 1.5 times 1 is still 1.5. And over here, this is going to be negative 4.5 times 5, which is going to be negative 22.5. And adding all that together, we've got, let's see here, 19. This is going to be 20.5 minus 22.5 is going to be negative 2. Now that we've used trapezoidal rule a couple times, we're going to take a look, as we did with the LRAM and RRAM, at whether this over or under approximates various curves. So take a look at this graph on which trapezoidal rule is being used and see if you can figure out what determines whether we have an over or under approximation. You think you've got it? So you'll notice here that we're decreasing and increasing in spots where trapezoidal rule is over approximating. And same thing here. Increasing, we're under approximating. Decreasing, we're also under approximating. So we can't look at increasing versus decreasing. What matters here, you might have noticed, is the concavity. When we are concave up, like this spot right here, that's always going to over approximate. Look over here again where we're concave up, over approximation. When we're concave down, like this spot right here, then we're always going to under approximate with trapezoidal rule. Given what we've just talked about, see if you can figure out if approximating this integral with the trapezoidal rule will be an under or overestimate. Pause the video and give it a shot. So with trapezoidal rule again, it's all about the concavity. So first off, we better make sure that this interval has just one concavity. If it does, then we can test a number from the interval to see if it's concave up or down, and that'll tell us if we are over or under. So we need two derivatives to figure out concavity on this. First derivative is going to be x cubed, then minus 12x squared plus 36x. Doing a second derivative gives us 3x squared minus 24x plus 36. And then, if we factor out a 3, inside we've got x squared minus 8x plus 12. So that's going to be 3 parentheses x minus 2, x minus 6, which gives us the critical values of 2 and 6. So these are the values at which the concavity might be changing. Between 2 and 6, and outside of them, we know it's always going to be consistent concavity. The interval from -1 to 1 is outside of the 2 here. It's everything. It's to the left of this first critical value. So we know that we have the same concavity throughout this whole interval. Now that we've established that, we can just pick one value from the interval and plug it in. I'm going to use 0. That seems pretty easy. So plugging 0 into my second derivative, I've got a negative times a negative, which is going to give me a positive. So that means we are concave up on that interval, which means the trapezoidal rule will be an overestimate. For your wrap-up, let's ponder the following questions. Is the trapezoidal rule an upgrade from the 3 rams that we learned before? And do we need rectangles anymore? Well, here's my 2 cents on this one. As far as being an upgrade, trapezoidal rule is definitely, for a smaller number of subintervals, more accurate than rectangles. I mean, let's be honest, you can fit trapezoids more easily under anything than rectangles because you're not limited to the slope of the top of the shape. Having said that, we did see that the trapezoidal rule is a little more cumbersome than RAM. The formula is a little more bulky. And also, as you increase the number of subintervals towards infinity, your increased accuracy from trapezoids isn't very much. I mean, an infinite number of infinitely thin trapezoids is not going to be any more accurate than a bunch of infinitely thin rectangles. They're all going to fit under pretty much anything you want. And if they don't, you just make them even thinner. But we still like to have this other way of doing things, and the AP exam will often ask you to use the trapezoidal rule. So there you have it. Until next time, this is Mr. Sutton signing off.